programmers, the people, the human beings, to write in English-like statements, okay? But the machine, it deals in zeros and ones, voltage, high voltage, low voltage. So now in the old days, the very earliest computers, programmable computers, people programmed literally in zeros and ones. And it was extremely tedious, and there were a lot of errors made, lots of bugs, as they came to be called. So that motivated people to change things. They said, oh, we have to make things more efficient. Programming in zeros and ones is just too tedious. There must be a better way. It pushed them, it motivated them to find more efficient ways of programming. And so the idea of writing high-level languages, as they were called, not low-level language, not low-level code. Languages like Fortran came out as one of the first, and the business equivalent of Fortran. What was that called? I'm forgetting. Anyway, decades ago. Then there was a need then for a translation program to take as input the high-level English-like text of the programming language and translated that into low-level machine code of zeros and ones. Right, and the software, this compiler, this translation software, it would use parsing trees as part of it. When the compiler looks at your input, the code, the high-level code, the English-like words that you're using in your high-level language, it needs to extract the meaning. It needs to understand what it is you want the machine to do. It needs to understand the meaning of your program. And to help do that, it will use a parse tree. Okay. So that's essentially what it's saying here. And this parse tree that the compiler will generate, okay, or a part of the compiler will generate, it generates that parse tree by using the CFG, context-free grammar, of the programming language that the user uses. Right? So you can see there's a close link between compiler theory and CFGs. These grammars. They're intimately linked. Okay. Now jumping ahead quite a bit, creating these parse trees for compilers. That's the theme of Ethereum, chapter 7. So way ahead. 0.16, and there's a problem in the same chapter, 7.43, right? And it talks about an algorithm, a set of steps, right? An algorithm that parses CFLs, context-free languages. Okay, so you'll have to wait a while, like 5 chapters. It's a good month or more, right? Or more, before we get to chapter 7, but we'll come back to this idea of using an algorithm that actually creates parse trees. So in other words, automatically. Okay? So, all right. Now a bit of comment here. This grammar, G4, our fourth example of a grammar, it's obviously just a piece of a programming language that can deal with arithmetic, with arithmetic expressions. It's just a small part of that programming language, an arithmetic programming language. And now, do you notice? I'm blocking a bit, but do you notice how these parse trees tend to group the symbols in a certain way? Like, for example, these 3 symbols got grouped like on the right-hand branch of the tree, so to speak, and these 5 symbols here, the 2 parentheses, the A's and the plus, those 5 symbols got grouped, and they sort of took the left branch of the tree, the parse tree. And does that remind you of something that you just know anyway, or something we talked about a bit before? I'll give you a hint. Keyword is precedence. Right? Remember precedence rules? Like say you have an arithmetic expression. 2 plus 3 times 4. What's the answer? Evaluate that expression. 2 plus 3 times 4. Is the answer 14? Or is it 20? Is that right? So is it 14 or is it 20? Well, without parentheses, without using parentheses, there's a rule of precedence that you operate on the multiply first and then the plus. So the answer would then be, now 2 plus 3 times 4. Oh, wait a minute. Sorry. Oh, 2 times 2. What did I say? 2 plus 3 times 4. Okay. You do the multiplication first. So 3 by 4, that'll give you 12, and then plus 2 gives you 14. So that's the answer. Okay. So the precedence rule. Precedence means which one you do first, which one has priority. So precedence rules, priority rules, same thing. So this grammar, the parse tree, in constructing the grammar, in other words, constructing the rules that belong to your R, the creator of this grammar, and that'll be the next big topic, in fact, on our next board, is actually creating grammars. In other words, designing grammars. At the moment, we're analysing them. Right? We're given the grammar and we think about them, we analyse them. That's easier than designing a grammar. But so the person who designed this grammar chose rules, substitution rules. Your members of, oh, you can't see it. Your members of big R in such a way that your parse trees have the same precedence rules that exist for ordinary arithmetic. Okay, so these, the substitution rules were chosen so that if you have brackets, then what's in the bracket, these symbols tend to get grouped into a particular branch of the parse tree, whereas if you have here no parentheses, well, then the multiplication took precedence. So these 3 tend to get grouped and took like the right branch of the parse tree. And that happened because of the choice of your substitution rules. So when you become a designer of a grammar, you need to be thinking about such things. So typically, a person who designs a whole compiler is usually quite brilliant, right? It's an art. It's quite a difficult thing to design a whole compiler, because you need to take all these things into account. All right. All right. Well, I've explained this, so that's the end of the session.